Hello all, this is Dr. Jagan, working as an associate professor in the Department of Electrical and Electronic Engineering and Vignan Institute of Technology. So in this video lecture, I am going to explain about three-phase full-wave controlled converter. Right. So in the last video, I have explained about three-phase half-wave rectifier, which is also called as three-phase three-pulse controlled converter. Three pulse means for one complete cycle, 360 degree duration, you can say, there will be three pulses at the output terminal. Now, in this lecture, I am going to concentrate on six pulse controlled converter. Again, six pulse means for one complete cycle, which means 360 degrees, there are six pulses at the output side of the converter, right? So this is three-phase six-pulse controlled converter is also called as three-phase full-wave converter, right? So now, if you recall, we have completed all these things in the last few videos. In the last video, I have discussed about this three-phase half-wave rectifier, which is also called as three-phase three-pulse converter. Right. So now I am going to elaborate about this three-phase full-wave converter, which is also called as six-pulse converter. Right. Now this is the circuit configuration for three-phase full-wave controlled rectifier with resistive load. Now you can say this is, you can say, the secondary of the transformer is connected to this bridge. The primary of the transformer is connected to three-phase supply. It can be a step-down transformer or step-up transformer depending upon the voltage rating of the source and the load. And you can see this is the R phase, Y phase, and B phase voltages, right? And this T1, T4 forms leg X, T3, T6 form leg Y, T2, T5 form leg Z. So there are three legs which controls the three-phase voltages, and the center point of each leg is connected to a particular phase R, Y, B, and so on. Right. And across the output terminal, we are going to connect a load here. Now I can see this kind of voltage we are going to provide from the transformer primary. And when you see at this bridge, the bridge is subjected to these voltages. You can see this VR and VR negative. Similarly, you can see VY and VY negative, right? So you can see these voltages. And now here you can find out the crossover points. These are the crossover points. So during this interval, thyristors, uh, uh, they are in forward bias condition. So now you can see this is related to R phase, and R phase, I can see there are two groups here. Now I can divide this into two groups. One is positive group thyristor, and here I can call it as a negative group thyristor, which means T1, T3, T5 are will be in conduction state when they will be having more positive voltage across them. Similarly, T2, T4, T6 uh, will be in conduction state when they will be having more negative voltages across it. Now we'll see all those things, whether which one is having more positive and which one is having more negative. Right. Now you can see here during this interval, I can say this VR. VR means leg X. It consists of two thyristors T1 and T4 and is related to positive voltage. So during this interval, T1 will be in forward bias condition because we'll be having more positive voltage across this particular terminal. So T1 will be in forward bias condition, T4 will be in reverse bias condition. And you can see from here to here, these are the crossover point. During this interval, it is related to Vy, and Vy thyristors are I can say Y leg. It consists of T3 and T6. So during this interval, T3 will be in forward bias condition because it is having more voltages across it when compared to more positive voltage across it when compared to any other phases. Again, from here to here, you can see the B phase voltage more positive when compared to any other phase voltages. So B phase positive group thyristor is T5. So T5 will be in forward bias condition. That is why I have mentioned there the forward bias condition of T1, T3, and T5 like this. Again, if you see the bottom voltages, here you can see during this interval, it's associated with B phase. And B phase voltage will be more negative when compared to any other voltage. So during this interval, B phase negative means you can say it is associated with T2. So T2 will be in forward bias condition during this interval. Again, you can see this is related to R phase, and R phase voltage more negative now, and which means T4 it will be in forward bias condition. And again, you can see during this interval, the Y phase voltage having more negative, which means T6 will be in forward bias condition. So now we know that during and I can say each thyristor will be in forward bias condition for a duration of 120 degrees. Now we'll see the combination because to get the current from source to load and back to the source, now one device should conduct from the top pair. You can say one should be from T1, T3, T5, and one should be from T2, T4, and T6. Then only there is a possibility that there is a closed path for the current and you will get some voltage. So that means we'll see the combination. Now you can see during this interval, T1 forward bias condition, T6 forward bias condition. Now you can say from here to here, T1 will be in forward bias condition. The same thing I am repeating here. So here to here, T3 will be in forward bias condition, T5, T1, T3 like this. Similarly, if you see the one more uh, column here, so here I can say T6 will be in forward bias condition, then T2 the same thing I am writing here. Then T4 here you can see, then T6 here you can see. So those will be in forward bias condition. Now to get control over the output voltage, I need to trigger the control element. Right now, to trigger the control element, I need to see which device will be in forward bias condition during that particular period. Now you can say, I told you that each device has to conduct for a duration of 120 degrees. Right. So now you can see each SCR will conduct for a duration of 120 degrees here. It is 120 degrees. 1 second. Right. So each SCR has to conduct for a duration of 120 degrees. Okay, that you can see here. Right now we'll see the pair of devices. So during this interval, T1 forward bias condition, no doubt. T6 also in forward bias condition. So I can trigger T1 and T6 to get some voltage across the load because they are in forward bias condition during this mode 1. Similarly, if you see in mode 2, where T1 is in forward bias condition, T2 will be in forward bias condition. So I can turn on them. And during this mode 3, T3 is in forward bias condition, T2 also in forward bias condition. That is I have drawn from the waveform. Again, during mode 4, T3, T4, during mode 5, T4, T5, during mode 6, T5, T6, mode 1, again T1, T6. So during this, for each 160 degrees duration, there is a pair of devices, those are in forward biased condition. Right? So let us, that means each pair of SCRs will conduct for a duration of 60 degrees only. Right? Now these are the combination. So now I can say in order to control and convert the three-phase AC into DC uh, for a 360 degrees for complete one cycle, there are 6 thyristors are used to control and convert this AC voltage. So 360 divided by 6 means it will be 60 degrees. That is why each pair of devices is conducting for a duration of 60 degrees. Right. Now you can see here, this is the procedure you need to follow. T1, T2, T4, T4, T5, T6, T1, T2, and so on. Right. I will tell you why I have mentioned like this. So I can say each SCR, right, T2 has to conduct for a duration of 120. Right. Similarly, T3 has to conduct for a duration of 120. T4 for 120, T5 for 120, T6 for 120, right? Like this. Now you can say the pair of devices will conduct for a duration of only 60 degrees. So here the 60 degrees may be during this interval, T2, T4, T3 will be in conduction state, remain 60 degrees, T3, T4 remain 60 degrees, T4, T5, like this, it is forming a chain like this. So, in order to get that idea, I have mentioned like this T1, T2, T3, T4, T5, T6, T1, and so on. Right. So, here now I can say for a three-phase voltages at this particular point, just after this particular point onwards, the R phase voltage, which is more positive when compared to any other phases. That means during this interval, the thyristor associated with the R positive, which is T1, will be in forward bias condition. So I can trigger T1 at this particular point. Similarly, if I trigger this one, there should be one device that should not be T4. T4 will be in off condition because T1 it is in forward bias condition means T4 should be in reverse bias condition. So either I can trigger this one or I can trigger this one. We'll see which device we are going to trigger during this interval. So we are going to trigger the device during this interval that depends upon which thyristor is having more negative voltage across it. I will repeat, depending upon the which device which is having more negative voltage across it, that device we are going to trigger, right? It may be T2, it may be T6, but it will be T6 here during this interval. I will tell you. That means at this particular point, from this particular point onwards, we can trigger the thyristor T1. Before that, you cannot trigger because if you see during this interval, uh, only the R phase voltage is more positive. But if you see during this interval, no doubt it is positive, but it is not more positive when compared to other phases. There may be B phase voltage positive, there may be Y phase voltage more positive, right? So we cannot trigger that. That means during this interval, T1 will be in reverse bias condition, and from here to here only the T1 will be in forward bias condition. Similarly, during this interval, the B phase thyristor will be in forward bias condition. B phase thyristor means can say T5. T5 will be in forward bias condition, right? We'll see all those things step by step. So the now in case of three-phase full wave controlled converter, the firing angle is measured from the crossover point. And if you project this crossover point on the omega t axis, at omega t will be 60 degrees. So at omega t equals 60 degrees, the firing angle is alpha equal to 0. And there is a relation between omega t and alpha. Now we will write in case of three-phase full wave controlled converter, omega t will be equal to 60 degrees plus alpha. Right? This is the relation in case of three-phase full wave controlled converter. Now let us say we'll discuss mode by mode. There are 6 modes here. I have mentioned here mode 1, mode 2, mode 3, mode 4, 5, 6 like this. So there are 6 modes and each mode will be for a duration of 60 degrees. 6 multiplied by 60 means 360 degrees. So in one complete cycle which is 360 degrees, there are 6 modes. There are 6 modes now we can see. Now during this interval where which is called which is called. So now we will discuss about mode 1. So this is mode 1. You can see from here to here, you can see at which omega t equals 62, omega t equal to 120 degrees. This is what mode 1. So during this interval, now you can see T1 already it is in forward bias condition. So T6 is also in forward bias condition. So during this interval, T1 will be having more positive voltage, T6 will be having more negative voltage. So those devices, they will be in forward bias condition. One from the bottom positive group thyristor, one from the negative group thyristors. Now T1, T6 they are in forward bias condition, and remaining all devices, they will be in reverse bias condition. So I can replace them with open circuit. Right now I can trigger T1 and T6 at simultaneously at a firing angle alpha. Now alpha is here, I will draw for alpha equal to 0 degrees. At alpha equals 0 degrees, the omega t will be 60 degrees. So from this particular point onwards, the output voltage will has to follow the input voltage, and you can see this portion. Right. So I have triggered T1 and T6 simultaneously. So T1 it is in on condition, T6 it is in on condition. It is at higher positive, and now you can see this is at uh, more negative. Right. The current always leaves from positive terminal, so it is leaving from R positive. Right. T1 anode, T1 cathode, load resistance. It is entering at this particular point, which is positive, and through T2 anode, T6 anode, T6 cathode, and back to the negative neutral, which is more negative, which is at more negative. So these are direction of current we may expect from source to the load, right? And this pair will conduct for a duration of 120 degrees, because just after this particular point, you can see one more devices will be in devices will be in forward bias condition, because you can see this voltage, right? So this is the condition during mode 1, and the load is resistive load. The current waveform you can see it with green color here. Similarly, if you trigger this T1 and T6 at alpha equals 30 degrees, so alpha 30 means omega t will be 90 degrees. So you can see it is starting from this particular point where you can see omega t equal 90 degrees. So from there is a sudden increment in the voltage, and it is following the input voltage. You can see, and it will conduct for a duration of 60 degrees. Now this portion you can see, as I told you that load is resistive load. In case of resistive load, the current and the voltage they should be in phase, because that's why you can see here the green color is for the output current, which is following the output voltage. Now let us move on to the next mode. Next mode will start from omega t equal to 120 to 180 degrees. We'll see here. So this is what the mode 2, and if you project on the omega t axis, it is from here to here, where you can see this duration 120 to 180 degrees. So during this interval, you can say here, during this interval, we will see which device will be in forward bias condition. Now I told you T1 it is in forward bias condition, no doubt. T2 also in forward bias condition, and because T1 is subjected to more positive here, and T2 will be subjected to more negative here. So those are in forward bias condition, and I can trigger them at any instant of time during this interval. Right. So now I will trigger at omega t equal to again at alpha equals 0, which means alpha is measured from the reference point. So from this particular point on, T1, T2 will be in for conduction state, and they will be carrying the load current. Whereas the other devices, T2 to T6, they are in reverse bias condition, so they will goes to off condition. So now you can see the equivalent circuit. Now T1, T2 are triggered at omega t equal to 120 plus alpha, where alpha equals 0. That is why from 120 to 160 degrees will get 180 degrees will get some output to across the load. So I told you that T1 is triggered, so it is replaced by short circuit. T2 also been triggered, and R phase voltage more positive, you can see. So current always leaves from positive terminal, it is leaving from R positive. T1 anode, T1 cathode, load resistance, T2 anode, T2 cathode, and it is connected to B phase, which is at more negative. Right. So now it is entering at this particular point. So you will get a positive voltage across the load in respect of the input supply. Now you can say during this interval, the output voltage you may get like this. And since the load is resistive load, the current and the voltage they are in phase. You can see the current waveform also. Now again, if I want to trigger the this thyristor at omega t equal to 30 alpha, which is 30 degrees. Now 30 degrees meant from reference point, it should be 30 degrees from here. And now it omega t will be 120 plus 30 means 150 degrees. So even if you project here, it will be 150 degrees. Right. So from this particular point onward, the output voltage will has to follow the input voltage. And since the load is resistive load, the current and the voltage they should be in phase. Like that you will get. So this is about mode 2. Now we'll focus on another mode, which is mode 3. Now you just focus on the conducting devices. Now mode 3 will start from, you can see this is what mode 3, and now you just trigger mark a line here. During this interval, T2 already is in forward bias condition. Now T1 is turned off because it will goes to off condition after this particular point onwards, and T3 will be in forward bias condition, which means T2, T3 they are in forward bias condition. Remaining SCRs T4, T5, T6 and T1 they are in reverse bias condition and they are replaced by open circuit. Okay, now I can trigger T2 and T3 at any instant of time during this particular interval, right? Because T2 is connected to more positive and T3 is connected to more negative here. So I can trigger these devices. So if I trigger these devices at omega t equal to 180 plus alpha. If alpha equals 0, you will get this portion at the output voltage terminal, right? And the current and the voltage are in phase, so you will get this portion, right? And if alpha equal to 30 degrees, 180 plus 30, it will be 210. So it will start from this particular point onward. From here, if you measure, it will be 30 degrees, and it will start from this particular point onwards. And is following the input voltage, which is a block color Y phase voltage. And since the load is resistive load, the current and the voltage they should be in phase. So this pair of devices again they will conduct for a duration of 60 degrees only, right? So now I will move on to one more mode, which is mode 4, right? You just focus on this particular point here. So this is what we are going to discuss. During this mode 4, T3 is in forward bias condition already. Now T1 is commutated by its supply voltage and the T4 comes into conduction state. T4 comes into forward bias condition. So I can trigger during this particular mode 4, I can trigger T3 and T4 simultaneously, right? And if I trigger those devices, you will get some voltage across the load, right? So now I can say T3 and T4 are triggered at omega t equal to 240 plus alpha. Alpha can be 0, alpha can be 15, alpha can be 30, alpha can be 45 degrees, even alpha can be 60 also, right? But the alpha should be from 0 to 60 degrees only, not more than that, right? So now if I trigger T4 and T3 simultaneously, this is the equivalent circuit. Now you can see during this interval, uh, uh, Y phase voltage is more positive. Now T3 will be in forward bias condition, and uh, R phase voltage is more negative. So T4 it is in forward bias condition because it is having more negative across it. So now I can trigger T3 and T4 simultaneously. The current always leaves from positive terminal. Now the Y phase voltage is more positive. Now here it is Y phase. The current always leaves from positive terminal. It is leaving from positive. T3 anode, T3 cathode, entering at this particular point, which is positive, and it will take the path like this: T4 anode, T4 cathode, and back to the R negative. Now R it is R phase voltage at more negative now. This portion you can say, and you will get some current due to presence of that current. You will get some voltage. Now you can see this portion, right? You can see this portion. Okay. Now at alpha equal to since the load is resistive load, you can see current and voltage they are in phase. Now at alpha equal to 30 degrees we want to do. So you need to measure the reference point from this particular point where alpha equal to 0. right? Because that particular device will be in forward bias condition from this particular point onwards. Now if I substitute alpha equal to 30 here, it will start 240 plus 30, so it is starting from 270 degrees. Even if you measure on the omega t axis, it will be 270 degrees, and it is giving the output voltage, right? Similarly, I can go for the next mode. During this particular mode, um, T4, T5, they will be in forward bias condition, whereas other device they will be in reverse bias condition. So I can replace with them with open circuit, right? And I can trigger the forward bias devices T4 and T5. They are in forward bias condition because you can see during this interval, you can see, right? T4 is having more negative, T5 is having more positive, so they will be in forward bias condition. So if I trigger these devices, they will go to conduction state, and this is the equivalent circuit. The current always leaves from positive terminal. Now B phase voltage is more positive now, so this is more positive now. So the current always leaves from positive, right? It is entering at this particular leg Y, leg Z, T5 anode, cathode, load resistance, and R phase voltage is more negative now. T4 anode, T4 cathode, and back to the R negative. So this is the direction of current which may flow from source to the load and back to the source. And they will conduct and you will get some voltage, right? So you will get this portion now. And they will conduct for a duration of 60 degrees. Okay. Similarly, you can have one more mode here. Right. So this is the sixth mode. In 16 mode, you can see here, this is associated with sixth mode, in which T4, T5 is in forward bias condition. It is already in forward bias condition. Now T4 is commutated and T6 comes into picture. Now that will be in forward bias condition. So to control the output voltage, I can trigger these two devices. So they are triggered at omega t equal to 360 plus alpha. If alpha equal to 0, the output voltage will follow from omega t equals 360 degrees onwards. 360 degrees means from this particular point onward, you can say, you can get this portion, and they will conduct for 60 degrees. And you can see the current waveform which is in phase with the output voltage waveform. Now, if I want to trigger these devices at alpha equal 30 degrees, so from reference point, if you want to measure, so this is our reference point. So if you measure from here, this will be 30 degrees, and you can see the output voltage waveform like this, and output current waveform like this, right? And except this T5 and T6, remaining all they are in reverse bias condition, and they will goes to off condition. Now you can see during this interval, B phase voltage more positive, whereas the Y phase voltage more negative. So now you can see it is at more positive. Now current always leaves from positive terminal, so it is leaving from more positive, which is B positive, and T5 anode cathode, load resistance. Now it is giving, it is flowing to T4, T6 anode, cathode, and now Y phase is at more negative now. So it is taking the path like this, and you will get some current. Due to the presence of this current, you will get some voltage. So you can see this portion voltage and current like this. So this is in 360 degrees interval. If you see the output voltage, you will see 6 pulses at the output side. Now if I consider here, right? So you can see 1, 2, 3, 4, 5, 6. So up this particular point, you can see this is associated with, if you consider the blue color input waveform. So it is completing one cycle. So which is 360 degrees. So during this 360 degrees, you can observe 6 pulses at the output side. So the number of pulses increasing means there is a reduction in the ripple. Now only this much of ripple is there. Only little amount of ripple is there. When compared to single phase and three phase half wave converter, the ripple is reduced a much, right? So the reduction in the ripple, and we cannot, you can reduce the reactance, filtering components, we can say, right? That is why if you go for more number of pulses at the output side, no need of going for what is called reactance, capacity filter or inductive filter, you can say, right? Now this is about three phase full wave control rectifier with resistive load. and you know the waveforms, right? So just now I told you that in one complete cycle, you can see from here to one to here. This is one complete cycle, which is for 360 degrees, or in other words, I can write 2 pi. So now I can calculate the average output voltage because they are triggered symmetrically. So I can consider only one cycle. I can consider only this much of portion. And this much of portion, there are 6 portions are there. So if I calculate the area under this particular curve, I can calculate the area under remaining part, and I can summarize that in one cycle we are having this much of area. So now to calculate the average output voltage, it is 1 by 2 pi because it is 360 degrees interval 2 pi by 6 means we are getting 6 pulses at the output side, and you can say uh, we are getting output voltage during this portion where I can set alpha equal to 0, it is 60 to 120 degrees. So if I substitute alpha equal to 0 here, it is 60 to 120 degrees. Alpha can be any value between 0 to 60. Now, I can write alpha plus 62, alpha plus 120, Vm sin omega t, right, is very with respect to sin omega t. And you know the integration of sin omega t will be minus cos omega t, right? And take Vm common, it is Vm by 2 pi by 6, and you just substitute upper limit or lower limit, and if you substitute the upper limit or lower limit, it will be 6 Vm by 2 pi minus cos upper limit alpha plus 120 degrees minus and minus plus cos lower limit alpha plus 60 degrees. It is just like a cos A plus B. Right, I can write cos A cos B plus sin A sin B, right? I can write like this. So similarly, now you just substitute cos 60, value of cos 120, cos 60, sin 120, sin 60 value. And if you solve this one, you will get the average output voltage as 3 Vm by pi cos alpha, right? Now, if I substitute alpha equal 0, I will get the maximum voltage across the load, which is 3 Vm by pi, 3 Vm by pi, right? Now I can also calculate the average output current if you know the average output voltage, which is 3 Vm by pi cos alpha. That divided by R will give the average output current, right? Similarly, I can calculate the RMS output voltage. So now I need to take root mean matlab 1 by 2 pi by 6 and square Vm square sin square omega t. The limits are alpha plus 32, alpha plus 120 degrees. Now I can take Vm square out of the root. Square root will get cancelled. Vm under root 1 by 2 pi by 6 and sin square omega t, we can write it as 1 minus cos 2 omega t by 2, right? You just separate these two words, right? Integrate these things and substitute the upper and lower limit, and you just substitute the values of cos as sine 2 into 40, substitute the values of sine to 120, sine 240, and if you do that one, you will get the RMS output voltage of this much, right? So if you know the RMS output voltage expression, you can easily calculate the RMS output current. So this is about the resistive load, right? Now this is you can see now this is for RL load. We'll discuss all those things in the next class, and this is for RLE load, right? All those things we will discuss in the next class. Thank you.